All right, you are all welcome again tonight. I hope you had a great day. I hope you've checked through all that we discussed since this week began. We'll pick it up from here. We're just going to wait a moment to allow other people join us. So if you are just joining yesterday, we started our machine learning journey and we understood what machine learning is all about, the types of machine learning that we have. We spoke about life cycle of machine learning, the things that we must see to know that indeed you understand all that it takes to build a machine learning model. And we talked about the other name for models to be algorithm. Then we spoke about the step to step also. And today we will continue from where we stopped, and we'll talk about outliers again today under our data cleaning. And kudos to people who have been sending in what they've been trying out, and thanks to the community of experts already who are also contributing, suggesting what should be done. I took our time to check that and I see the amazing work happening in the community, and that's also very good and fantastic. Please let's keep that momentum. It will continue to help and continue to guide us through it. Just waiting a moment to ensure that a number of people have joined before we continue from where we stopped. If there are questions, we quickly take that before we commence tonight. There are questions from the last class. Okay, so let's just continue. Others will join us so that we can keep moving. So we start today from outliers, and like we established yesterday, and some people were also asking on the group, the role of adding outliers is to be able to plot and see the extreme value, the value that is not like normal to other ones. For example, here we want to try and check out, and don't forget that this outlier will always be on features that are numeric. All right, there have to be numbers. It's only numbers that we have extreme, right? So if the numbers have been 1, 2, 3, 4, 5, 6, and all of a sudden you saw value 70, something must have happened. So that is not as if it's wrong, but then we need to be able to understand what really happened. Why did that happen? Maybe it's sales, for example. Was it because it was a festive period? What happened that day? Was it that somebody special came to our company to buy our product? It will be useful for analysis, but when we want to build our machine learning model, we need to drop any value which are extreme values right now. So here now you can see from the age, we plotted the age as a box plot. So if you look at this now, you see that we have most of the age less than, if you look at this now, the ages here are less than 5. A number of them are here. This is the mean, that's the average of most of the age that we have. On an average, the average here is 30 of the ages that we have. You can see the plotting and all of that, but you can start seeing, this guy here, much like standing alone, that gives you a picture of outlier. And also most time we plot like a scatter plot. The scatter plot will also give us a clearer picture, to what we have. All right. Scatter plot will also give us a clearer picture. Let's just say you want to plot scatter plot and you don't even know how to write the code like I showed you yesterday. Once you know what you want to do, you can always ask online and you will see sample of code to do that. All right. So this is an approach of checking your outliers. As we move on, we will check how we can, as we move on, we will check how we can then remove them. All right, so another key thing to look at is data validation and verification. At this point, after you have cleaned your data, after you're still in the process of cleaning your data, after you have done the needful, you want to let us know what are the features that are our inputs now. So you can see that we define all those features that our input into our X, while the Y is supposed to be our output. Now, why are we having the output in this result? We're having output because it is a supervised machine learning problem we're trying to solve. That means this survived is the target. We're trying to predict the survive. And don't forget, when we checked yesterday, what are in the survive? Did you survive or not? All right, is that you yes or no? 0 and 1. That is the picture that we have here. So what we have here, after we have done some cleaning, is to tell us, even though we have many other features, don't forget that, but these are the ones that we think are relevant for the kind of project we're working on. So we can always do this, all right, like that. For our X, you will always have your X, and don't forget, in this context now, our X is our input, is our features, while our Y is our target. The one we intend to predict is our Y. Okay, and also finally, for this particular material, we look at data formatting. Data formatting involves converting the data into a standard format or structure that can be easily processed by the algorithm or the model for analysis. Here we will discuss common use data formatting techniques, and some of the data formatting techniques we will talk about here is scaling and normalization. Like I have told you, of course, when you have numeric features, even when you have categorical feature, we should talk about that. We will talk about that under feature engineering. But for now, know that we are also going to change the scale, and we are going to normalize our data, because, like I mentioned to you earlier, that when we're trying to build our model, whether we have numeric feature and we have categorical feature, the one that are categorical, which are objects, we also have to also convert them into numbers. And don't forget that numbers, binaries that we know, are typically between what, zeros and one. So the goal of formatting, which is either scaling or normalization, is to transform the value to a specific range. And of course, for your scaling, most of the time, and of course, from the knowledge of your binaries that we know, our computers works with bits, right? So at that point, the range is converting it to is zeros and one. Is zeros and one. So some common scaling methods that we will talk about this moment. One is min-max scaling. So the min-max scaling rescales the value to a specific range, typically between 0 and 1. It preserves the original distribution and ensure that the minimum value we have is mapped to 0 and the maximum number we have is mapped to 1. So the range, when we are doing scaling, the value we are going to get is going to be between zeros and 1. That's the value we are going to now have in our data. All right. So now we are using a particular method, or a particular method from the sklen. So for the models we are going to work with, there is a new library we are going to work with. All right. I'm still going to introduce that properly when we get there. But for now, just to take note, the library, just like the same way we have been working with pandas and all of those guys, the library we are going to be working on for our model, for modeling, or you call it for our algorithm, is called scikit-learn. And of course, this scikit-learn is also available. This scikit-learn is also available in our Anaconda Navigator. So if you are working with Anaconda Navigator, you don't need to install it because it was already available with us. All right, it's already available with us. Okay, it's already available, so it's already there. You don't need to install it. You just need to import it. So to use it specifically now, we want to use a preprocessing. All right, and the one we want to use this time around is min-max. So we say from sklen.preprocess, we want to import min-max scaler. Don't forget, what is min-max scaler is one of the way we scale our data. Now the scaler, now when we call it, we call the name of the objects, we call the name of the library, the function, like the way we used to do before, when we used to be the one to create it ourselves. But this one, we are already using built-in methods. All right, so we are calling the name min-max. Now this min-max is expecting some parameters. All right, so when you try to load So you can see what is happening there. I meant to like reload most of the things I'm doing here again. I'm not sure I closed my system. I didn't close all this part to work today. So I think the part I need to run is this part, X and Y. Okay. So all things should be equal at this point. But what I wanted to show you is that when you are working with a library, once you are sure you have imported it like this, when you call that particular method and you do shift tab, you'll be able to see all the expected parameters there. Shift tab is what I press when you have the, because most times you might not even know what a particular library can do. But when you call it yourself, all right, min max scalar, when you look at this now, when you come to the side, open and close bracket, you do shift tab, that is expecting a feature range, is expecting a copy or clip force. And of course, the good part is that you can read about what each of these things means here. You can see examples. You can understand even before you try it out. So if you look at it now, look at the example, how to use it. This is how to use it. And of course, the data, you can see the data is what is numeric because it has to be numbers for it to work. And you can see how they are saying scalar. You are calling the scalar. Then they are fitting on that scale. They fit on that scalar. All right, you can see it here. And after that one, they transform the data. And you can see this is what the data is by default. But when the transformation was done, you can see how the data looks. It's now going to be within the range of 0 and 1. That's the, the big picture. So look at what we have here. We created a variable called num column. All right, if you look at this now, you can see num column. So we are saying that it should select all the columns from our X, these guys, and of course, only the ones that are numeric. You can see not object. That is, don't forget we already established that we never want to use all these guys, all this formatting, all this scaling and normalization. It has to be on features that are numeric. All right. So if it's going to be on feature that's numeric, is that I mentioned this feature that are numeric, or I use this method to say loop through these columns in column X. If any of this guy is not object, that is, if it's not object, that means it's going to be integer or float. All right, based on what we have here. So you can see P class, sex, age, SPS, SIPSP, patch, that's the number of parents, fear, the fear field, and backed, all right, where they join from. So it's going to check through all of those guys and it's going to select only the ones that are not objects. And you can see when it selects them, we are storing that the value of our X now, X1 now we store it to be X, everything here. Same thing here. After we have done that and we have stored those column inside num column, all right, and of course we have also stored all our X, this guy here, inside X1. The next thing we need to do is to now fit it. After we have selected, the only way to see that we have done transformation is that to do fit first and do transform, or do it together by doing fit transform. So what are we transforming now? We are using this scalar which we have declared here, all right, but fit transform. What are we fit transforming? We are fit transforming all the columns that are available in num column, this guy here. And if you look at it here and we run the edge for X1, you can see the value has changed. How do I know the value has changed? Let's do for X alone and see the value. Let me do X.head. Look at X.head. All right, you see a lot of values here. Okay, but here, you can see that the value are, especially for the features that are numeric, all right, the value has changed within 0 and 1. Of course, you might be thinking, nothing but because we have already transformed it, all right, we can be sure that the value has changed to a range between zeros and 1 whenever we are using min max scalar. Somebody want to ask, when should I use min max scalar? The job is to experiment, all right. You are experimenting the process, all right. You are experimenting the process. So if you are experimenting, you try as many as possible out. So the next one you can try out is what? Scalarization. All right, you can use the Z-score scaling. It's still going to give us a transformation value that has its mean between 0 and standard deviation to be 1. So it's still going to help us. The goal of this guy, don't forget, the goal is to be able to help us prepare our data for the model. All right, prepare our data for the model. So with this now, we have looked at the most standardized way of cleaning your data. All right, the most standardized way of cleaning your data. I know some of these things might you are hearing them for the first time. Just take note of what I'm saying. Take note of what you are doing in the class. It's going to be handy as you begin to work. It's going to be handy as you begin to work. So let's move to data pre-processing now. Very close to what we have done. My screen is not clear. Okay, let me just make it a bit bigger. But you can also do that from your end. Okay, so let's talk about data pre-processing. We've already talked about that already. Gradually, we have said it, but we just want to look at it again from a right context. So data pre-processing is the first step in any data analysis or machine learning pipeline. Don't forget, this material is also inside my data cleaning, all right, folder. It's inside my data cleaning folder, just in case you're looking for it. Once you get to your ML, you see data cleaning. So most of the file I'm using is still inside my data cleaning. Somebody is asking, how do I know the best scaling method to use? Is experimenting. You try as many as you can, and when you now build your model and you see the result, you will know if that scale was okay or not. Even at times we might not even do scaling and normalization and build the model, all right, but then they all have their effects. So it is how the model perform that tells you. So the best approach is always based on the model, the outcome of the model. You will not, but what we have shown you are the things you should have done, whether you know or not, whether you have seen the result or not. All right, is always what to try out. So is modeling, these approaches are experimenting, so try them out. When you know what is best is when you now look at your results. That time when you now even build the model, that's when you are going to be able to conclude whether what you have done is right or not, or if there is something you need to improve on or not. I'm trying to check if there are questions there. So what is asking, how do we do the data to use scalar? Or I've mentioned that scaling will be used on numeric features. All right, you use scaling on, so at that point every of your feature must have become numeric. All right, so you use it on numeric features. Okay, so let's talk about so let's talk about preprocessing. Okay, so preprocessing is one of the first steps in any data analysis and machine learning pipeline. It involves cleaning, transforming, organizing your raw data to ensure it is accurate, consistent, and ready for modeling. So why does data preprocessing matter? One, it helps you to improve learning, whereby your model performs better. Your models performs better. Also, your model performs better, enables model performance, and of course, it helps you to also understand your EDA. So let's look at this process through. We are importing the necessary libraries. We import pandas as MP, numpy as PD. From of course, from sklen dot processing, we are importing minimax scalar, and we are importing standard scalar. We are importing cborn as sns, batchwork So the data we are working with is already here. You can see that diabetics, so you don't need to disturb yourself with the directory. So if I run this, it's going to show me all the data I have. So you can see I have pregnancy, the glucose, the blood pressure, the skin thickness, the insulin, the BMI, the diabetes predictive function, the age, the outcome. So this outcome is my target. All right. So this means if this person has diabetics or not. One will mean it has, zero will mean it does not have. All right. The next thing to do, just to use a data set to follow the processes, check some information about it. df.info shows each of the features. Pregnancy 765. We have how many entries? So this already gives us that there are no missing value here. There are no missing value here. There's no missing value here. You can see that all the data are no missing data. So I'm just doing this df dot is none dot sum. All right. You can see here now. So I don't need to fill any data. Why? Because there are no missing data. Are you getting it now? So what you do is primarily based on what is available in your data. All right. It's primarily based on what is available in your data. Okay. It's primarily based on what's available in your data. So if you look at this now another key thing we can check out is some statistical values in our results. So we can use our dot describe. Now, what will the dot describe method do? It will show us some statistical information about features that are numeric. Shows some statistical summary about features that are numeric. All right, that are numbers in nature. So if you look at this, we have the pregnancy, we have glucose, we have blood pressure, we have skin thickness, we have insulin, we have BMI, we have diabetics, we have age, we have outcome. So the count means the number of records there. So you can see that we have 768 pregnancy record, glucose, 768 records available in our glucose features. In the mean talks about the average. So on an average, we have about 3 to 4 people who are pregnant. On the average value for glucose is 120.1 or 121. The average values in our blood pressure is 69. The average in our skin thickness is 20.5 or say 21. Insulin is 80. You can see that standard deviation for each of them also the minimum. So that means that there are people who are not pregnant. That means there are people who do not have glucose is 0, blood group is 0. That's the minimum you have there. But the minimum age we have is what? 21. Right? The minimum age we have is 21. The minimum is that there are no people who have because that one is a categorical in nature. There are no people who has diabetics. 25 percentile, 50 percentile. 50 percentile is very close. It's the same thing as the mean of the distribution. 75 percentile, for many of us who have done a bit of statistics, you know what these languages mean. You have the quarter, you have the Q3, Q2, Q1. Q1 is 25%. Q2 is 50%, which is also the same thing as the mean. 75% is the quarter 3. The maximum value there. The maximum value in our pregnancy is 17. Maximum value, all right, the highest value you have in glucose, the highest glucose somebody had is 199. Highest blood group, so that's what those guys mean. The highest age in the data is 81. All right, so that means age is between 21. The records of people who have collected here is between ages of 21 to 81. All right, that's what we have here. Now the next step we are doing is to visualize our outliers. All right, to visualize our outlier. All right, is also something you might want to look at. So from here we have, I'm doing a plotting Like I said, we don't have all of the time to start explaining the code line by line. But what we're trying to do here is that we're trying to loop through the length of our columns. How many columns do we have? If I do df dot length, if I do this, because these are some of the things you should be aware by now. If I do this guy, so this length shows the number of records that we have. So when I use this length now, is to get the number of records. So now that means if I now put dot column here, is to get what? The number of columns. All right. So this shows that we have 9 columns. Don't forget, yesterday we spoke about some of these key things. df dot shape will show us the number of rows and columns that we have. You can see here 768 shows that we have 768 records, which is same thing as row, and 9 columns. So what we are doing here is that we want to draw some subplots of all the length of the column, which is 9, right? And the size, the fixed size of each of these plots should be 7 by 18, and the dimension ratio should be 95. You've done a bit of visualization before now. So for I and column in enumerate, I and column in enumerate df columns, plot on the axis, box plot, and the y label should be the name of the column. All right, the y label should be the name of the column, the tight layout, and show it. So you can see I plotted all of the columns that we have here. All right, see I plotted all of the columns that we have. Box plot, I've told you, this is the beginning, this is the end. All these ones are picture of outliers. There are not many people that is only happening at some point. This is the start, this is the mean, this is the end. All right, this is the end. All these ones, they are just happening at some point. All right, same thing here. This is the start, this is the end, this is the mean. These are some of the ways to interpret a box plot. All those ones you are seeing, they are pictures of outliers. They are pictures of outliers. All right, when they stand alone like that, especially extremely, they are pictures of outlier. You can see the start here. This is the average, and this one you can see the skin thickness when it is 100. You can see it is not every time. It's just a situation. It's just a situation that occurred. This is a picture of outlier. All right. So we check all of them here. So the next thing you want to look at, is how to remove the outliers. So we say here that removing extreme values beyond a reasonable range. So it doesn't mean that all of them are outliers. So these ones are still normal numbers. They are still within the range of these ones here. But the one that is extreme, maybe like this one now. Look at this insulin. Look at the values we have here. But this one is already going to like 900. That is a picture, extreme numbers. All right, extreme values. That is not like the normal values that we used to have. That's a picture of, this is very close to 850 or 900 thereabout, since the scale is 200. So this is very close to 900. So that is an extreme case. All right, that means there are some extreme cases in this insulin. All right, based on the range, based on the values that is plotting. All right, based on the value that is plotting. Based on the value that is plotting. So once you have extreme values in your plot, and of course what will help you to know that is your range. You can't really call these one outliers because they are within the same, is 60, 70, they are still within the same range. These are just showing that you have fewer values that are within 50 to 60 and fewer value between 70. But this one, for example, this insulin now, you have an extreme number that does not even exist than that certain time based on the range of your value. So this insulin shows a little bit of outliers. So to remove that, we need to do some little calculation of our value. And of course, I've told you most of the things you are getting in your box plot. Let me show you that again. Is your Q Q1, which is the 25 percentile. Your Q2 is this guy, which is the mean. Your Q3 is the what's it called now? The highest is supposed to have naturally. All right. So these are the guys you are going to subtract from to get your result. So to remove extreme number, your IQR, Q3, which is the 75 percentile, minus your Q1, which is your 25 percentile, the value below Q1 minus 1.5 Q, or you do. So these are the possible ways of removing outliers to get the lower value and get the upper value. So if you look at what we have here, we are saying that Q1, so if you look at what we have here to calculate that, we say Q1 and Q3 MP percentile for our insulin, 25 will go into Q1, 75 will go into Q3. It stores that value for all the values in our insulin. Then we created a variable called IQR, which is the difference between the two. Is going to be whatever the value of Q3 is minus Q1. To get the lower case, we will do Q1 minus 1.5 times whatever our IQR is. To get the upper band, we will do Q3 plus 1.5 times IQR. So these ones are, general calculation, all right? They are standard calculation that you need to do to undo such cases, all right? They are general calculation that you need to do to undo such cases, okay? So now to get a clean insulin now, we are putting that in a variable called clean underscore DF, and we are saying that DF insulin should be greater than or equal to whatever the lower value is, while DF insulin should be less than or equal to the upper. So this, please take note of the syntax. This helps us to remove, with this now, with this calculation that we have done, it will have removed all those outliers. This approach will have removed all those outliers, all right? It will have removed. So if you have another feature, another column that has that, you can copy this code and do exactly the same thing. Just change the name of the column that has, let's say for example, maybe age has it too. You just change this to age. This will also help you to undo such case, all right? This also help you to undo such case. So these are things we need to take note as we work. Okay, so that is one of the ways to undo outliers. Now, one other thing you want to do is to understand your correlation. Now, what is correlation? Correlation is the relationship between your features, which is your input, and your target variable, which is your outcome or your output. All right? Correlation is that time that you understand the relationship between your feature, because this will also tell you some of the features that you might need to drop. This might also tell you some of the features that are not going to be useful, in the tasks, in the projects you are working on. Like we mentioned yesterday, that okay, yes, we will know, the expert will be able to tell us the features that are not important. But also is that this correlation based on your input features, specifically at this point, the ones that are numeric, it will give you an idea of what is happening. So correlation helps to guard feature importance. You will know the features, the inputs that are going to be useful for your model. All right. Same thing when we are working on this, it's also going to plot all your features, specifically features that are seen to be numeric. Features that are seen to be numeric. All right. Numbers. Now it's going to plot. Now correlation is going to show every feature over itself. You can see it's going to plot all the feature in the x-axis and also on the y-axis. All right, I'm going to reduce this a bit so that we can see all the values. Yeah, so it's going to plot this both. Can you see it's plotting this guy on the y-axis and on the x-axis. Now for any feature to other feature, is either it is positive, is that it is negative, or it is neutral. A feature can either be positive, negative, or neutral. Some people also call it highly skewed, neutral, and all of that. But in simple word, a feature correlation can be negative, can be positive, or can be neutral. All right, correlation can be positive, can be negative, or neutral. So now the first thing to note is that if you see any feature to itself, every feature to itself is going to be 100%. So that's not our worry. For example, you see pregnancy to pregnancy is showing 1.0, it means 100%. Of course, you don't need that for anything. If you see glucose to glucose, you see 100%. You don't need that for anything. Blood pressure to blood pressure, 100%. So you see that it's going to create like a diagonal, which means that a feature to itself will be 100% correlated. A feature to itself will be 100% correlated. A feature to itself will be 100% correlated. But that is not the one we want to test. The one we really want to test are the features over our targets. And how do I know targets in the problem? First thing first, based on what I've seen over time, your target is always like the last features. It's always the last feature here or the first feature. So, but most cases, your target will always be the last feature. All these ones here are our X, while this guy is our Y. Most cases, all right? At this stage, that's one of the easiest way to know the target for whatever problem you're trying to solve. The target for whatever problem you're trying to solve. So that is the one we want to really pay attention to. As much as we can pay more attention to anyone over each other. For example, let's look at the pregnancy. Pregnancy and glucose has about 30% correlation. It simply means that glucose has 30% importance to pregnancy. Blood pressure 14%, which is not bad, is still positive. It shows that it has about 14% importance to understand pregnancy. And of course, people who have been pregnant before, who are married, who are people who are pregnant, you know that when they are pregnant, they ask them to go and check their glucose level, to check their blood pressure level. All right, these are information they take about them. What I'm saying now, I'm saying it because possibly I have somebody who is pregnant around me, or maybe because I'm a doctor or I'm a medical person, I'm able to say those things, or maybe because I've made my research. All right. So how you are able to interpret your result is based on how much you have understanding about the subject matter. Skin thickness is negative. That means skin thickness has no correlation. All right, has no correlation to pregnancy. Insulin has, of course, it doesn't completely mean that is the real thing in the real world. But as far as this data is concerned, that is what the result is saying. All right, as far as this data is concerned, that is what this result is saying. All right, as far as this data is concerned, that is what this result is saying. Now, BMI has about 0.01 or say 0.02, which is very low. Of course, it still has some little but very small, right? Diabetes predict function, you can see is negative. Age, so that means age has a lot to do with pregnancy, and of course, you know that too, right? So that is why our ages we expect people to be before they get pregnant, and that is why you see that we have laws that guides ages before people are pregnant and all of that. Okay, so age, we can see from here that age has a very high, about 54%, all right, over pregnancy. And outcome, which is like our target, has about 22%, which also shows that pregnancy is important to determine if the outcome of is diabetics, right? It has, but of course, you can see that it's not as if it has so plenty. It's just about 22%, which means that it's not as if being pregnant is a very serious factor in knowing, if somebody has diabetics or not. But if you look at the outcome for glucose, you can see it has what? About 47%, which means that glucose has a very high tendency to determine, to predict if somebody will have diabetics or not. So please, this is a very, very important concept too. All right, this is a very, very important concept. What I'm doing now is what you must understand though. What I'm saying, you must understand what I'm saying though. Please, what I'm saying right now, you must understand it though. Because if you don't understand all of this, you cannot do much with your data. And these are some of the things that will start giving you information. Some of the things that will start informing you about what to do, all right, about your data. And you can look at the next one. You can see blood group. Blood group has about 0.06, which is less than 1%. You can see that blood group has nothing to do. That is how you can interpret it in lay language. That this has nothing or very less importance or less correlation to outcome, somebody having diabetics. While insulin has about 13%, which shows some level of correlation, but it's not too much, about 13%. The BMI shows about 29%, all right, which shows a very high, and that's the mass index of the body, right? And of course, I do have some level of health background. You know what BMI are? They are very important indexes in human body. Why for diabetics predict function, it has about 17%, which also shows that it's important. Why for the age, you have about 24%. So from what you can see now, you can see the features that are important. Pregnancy seems to be important. Glucose, very, very important. Skin thickness, important but very low, is not negative, all right? But what we can see, they all seems to be important, all right? Even though some of them are high, some of them are low, all right? Some of them are high, some of them are low. Some of them are high, some of them are low, okay? So from what we can see from these features now, we can see that all these features seems to be important. Of course, glucose outcome to outcome is of no need. So that is what is happening here. The other thing you can do is that we can decide to also plot this thing so that we can see it. So here I want to plot an heat map. An heat map will give me a picture, of what it looks like. I first pass my correlation inside this one. I store it here. Then I want to plot an heat map to be able to see the correlation based on color. I'm running this one. Might take a bit of time. The heat map or pair plots might take a bit of time when we are plotting them. So same thing is happening here. You are plotting everything and you can see the correlation. You can see how the colors will change. Between here and here is 0.1, 0.2 here, 0.4 here. When you see this color, so when it's very thick, it is 1.0. When it's within this color is 0.8. When it's within this color is 0.6. When it's within this color is 0.4. So if you look at all this, don't forget your focus should be on your focus should be on your target, which is this guy. So, and of course, for people who might not also see color clearly, all right, you can just pay attention to this correlation table. So any of them will give you the expected result. Any of them will give it your expected result. Or also, you can do this on your correlation again. You can also print this. They are all approaches you can use to get your result. So we can see how important they are now. Can you see this now? This guy can tell you, can you see this? Is giving you the important ones. Glucose 46%, BMI, you can see them. Age, pregnancy, you can see it as ordered the way they are important. Of course, outcome is not necessary because it's the feature to itself, and every feature to itself will be 100% correlated. Every feature to itself will be 100% correlated. All right. So once you have been very sure that these columns are important or they are useful, this approach will also show to you a feature that is important. It will also show to you a feature that has no importance. So at least to a good extent, as a machine learning engineer, you also can use this style to know a feature that is important too, as much as you can also depend on the expert to tell you based on their own knowledge. With this kind of problem now, a doctor can tell you by just glance, even when we're not looking at your results, because they understand what those features means in the health world. All right, is a lab scientist, a nurse, somebody who is an health officer will be able to tell you this. Will be able to give you some insight, even into this part of the story. All right. So if you go back to this, those are some of the things you can do. Now, the next thing is, after you have checked that, you can also try to understand your targets. All right. Our target for this kind of problem now, for example, is 0 and 1, which shows a picture of a classification problem because it has the label to the category. So I'm plotting a pie for that. And I can see that diabetics has about 65%, and not diabetics has about 35%. All right, that is what is available directly now in the data. That's what is available directly now in the data. Now the next job is to now separate my data into the input and outputs, very close to what we did the other time when we were doing data cleaning. So this time around, when you want to split your data, once you know the important features, the only thing you are expected to remove from it is your target. Your target should not be in your X. Your target should be in your Y. All right? The target should not be in your X. The target should be in your Y. So the easiest way, instead of mentioning them one by one like we did here, instead of mentioning the feature here one by one like we did here, you can just do what I'm doing here. Just say df.drop. The only column you want to drop from your df is just the outcome, which is your target. I can see that we do not drop it permanently. We just drop it for a while. All right, we just drop it for a while. Then in our y is our target, our outcome, which is our output. So in our x we have all our inputs. In our x we have all our inputs. While our y most times is just one feature, which is our target, our label. Our y is our output. Of course, we also can call our input what? We can call our input features. We can call it independent variables. And of course, our output can be called target, can be called label, can be called dependent. So what does that dependent? It simply means that for us to predict if somebody has diabetics or not, we need all these ones here. We need to check the glucose, the BMI, the age of the person, the pregnancy, if somebody is pregnant, diabetes, pedigree, function, insulin, skin thickness, blood pressure. So with all of these guys, we can predict if somebody is going to have diabetics or not. All right. So that is what we are doing at this stage. Okay, so the next thing you can do at this point is to now scale. All right, we can now decide to scale our data. Don't forget we have split our data into x and y. What is the purpose of the scaling? The scaling is to now have our numbers. The scaling is to have our guide in a range, and that range will be between what? Between 0 and 1, like we are seeing here. Normalization, we scale our feature between 0 and 1. Good for algorithm like KMM and neural networks. And of course, in this class, we work with minimum max from our sklearn, and we use fit transform to learn the minimum from the data and apply scaling to it. So scalar, we call the minimum min max scalar. Don't forget we imported that when we are importing our libraries here. You can see it here. We imported it when we are importing our libraries here. So from here, we can see that we imported it as an object, so that we will not be saying min max scalar. We just be saying scalar whenever we need it. So this is what we need for the scalar. Then the next one is the normalization. All right, the next thing is the normalization, and that to do that we'll use the fit transform. So when we say S standardized is scalar.fit transform, this method will help us to do both scaling and transformation. So if we run this now, which is our X underscore standardization, we want to see the first 5 records there. If this happens, this will throw error because I've not run these parts. So you don't just go and run the parts. You have to, every code depends on each other. So let me start from here. Okay, so you can see the scaling that is doing. Don't forget that the scaling is going to give what is going to be between 0s and 1. That's the value we now have there. So if we do this guy now, okay, you can see the scale of the values we now have between 0s and 1. This helps the model for you. Imagine what is the meaning of this. This helps the model to perform, because this is what it understands, not those big numbers that we have there. This is what our model understands. So this is the best form to pass your data into your model. That's the easiest way to explain this. This is the best form to pass your data into your model. This is the best form to pass your data into your model. So let's take some questions before we go on our 10 minutes break. Somebody is saying, are you going to gather the data yourself? We have established this yesterday. If you are working on a project at the class level, we give you the data to use. If you are working in a company, they will give you access to the data there. If you are working on the project yourself, you can look out for data yourself. You can try to do data collection yourself. What is most important is that your data is somewhere. You're getting your data from somewhere. When determining the feature importance, should we compare it only target variables or all variables? I don't understand your question, but check your features, all your values, all your columns that are numeric specifically at that point over your targets, because you want to see how they are doing. If they are important to your target, is what you're trying to check out. So you want to check it over each of them, and it's the same interpretation. I've already explained that you can listen to that again. That's I took our time to explain what that means. So please, what's the difference between the mini scalar and scalar, and why do we use the two of them? They are two different preprocessing you can do on your data. That's the first thing to take notes. So scaling is necessary for standardization, and the other one is necessary for normalization. So, but of course, the two of them, they will generate a scale of zeros and one. While for your normalization, it also gives you a mean value of 0 and a standard deviation value of 1. But the simplest way, because I know that's a lot of words, is that these approach are necessary to pass your data to your model. You need to scale it. It's the scaled version of the data that the model will need to work with. So when working, we could just copy and paste the code and edit our values, something like that, exactly. So just know that you need it and know why we are using it is the first thing to take note of. Okay, so we will go on break now, and by 8:05 we'll be back. By 8:05 we'll be back from our break. But of course, if you still have questions, you can drop it. So see you again by 8:05. All right, welcome back. So from what we've seen, you see that we don't just get into building our models. There are pre-processings that we need to do. Once those pre-processes are well done, then building a model will not be too much of an issue. So we move to the next thing to do. We're already doing it. We just want to learn about it in more clearer and deeper concepts. And that is feature engineering. So yeah, what are we doing? So let me make this bigger. I make small the other time because I wanted you to see something from the go. So feature engineering, the things that should come to mind, we're already doing that, is that scaling, normalization, and standardization. So feature engineering is the process of, first thing is that we can create new features, we can transform already existing feature, and we can select the most relevant, that is the one that are important for what we are trying to do, from raw data to improve our model performance. Well-designed features helps machine learning models recognize important patterns and relationships, directly influencing how effectively the model learn. So why is feature engineering important? Why does it matter? One, it helps us to improve the learning. It enhances accuracy. Here, it reduces the noise, irrelevant information, leading to better predictions. Also, it helps us to prevent overfitting, emphasize meaningful signals, helping model generalize to unseen data, simplifies interpretation. Here, we can create more informative and understanding inputs. There are several techniques we can use for feature engineering, which include scaling, normalization, and standardization. So below are some of the most common ones. We have done them before. I won't just bore you with too much mathematics behind them, but in real sense, we can pay attention to the value. So when we do absolute, the same way we have done minimum, minimax scalar, we can also do absolute maximum scalar. And here, the value when we do absolute maximum scalar, the range of the value will be from -1 to 1. Don't forget, when we're doing minimum maximum scalar, it was from 0 to 1. When we're normalizing, our mean was 0 and our standard deviation was 1. Those are just the differences you will get there. And of course, each of them has when to use them. So the key characteristics of using absolute maximum scaling, it will scale values within the range of -1 to 1. It's also simple to apply. It's also high sensitive to outliers. So in their case, the outliers is going to undo them within our code. So here again, we are working with another data set. So you can see that I'm giving you more data set to use. And of course, each of them you can decide to clean them and prepare them for your modeling, right? And prepare them for your modeling. So here now, we are loading the data. And you can see from here, we want to only select only the data that are numbers. So that means there might be other features that are not numeric, but because of our minimum max, because of our scaling that we want to really learn, that's why we're only selecting the features that are only numeric and all. I'm just saying which one comes first between normalization and standardization. You standardize first and you normalize, all right? Standardization comes first, you normalize it. That's why you are seeing fit transform. The goal of the fit transform is primarily for you to have that result, okay? All right. So from here, we are trying to load a data set called housing, and we are only selecting only features that are numeric, so that because like I told you, all this scaling, all this normalization can only happen on features that are numeric. They can only happen on features that are numeric. They can only happen on features that are numeric. So please let's bear that in mind. And let's take note of that as we move on. So for because of what we're trying to do, you can see here we have average area income, average price, area house age, average area. But let's say I did not put this guy, so you can see that there are many other things there. All right, we just want to have, you can see that there are many features here. Can you see that? There are many features here. The only thing that I think the only thing that is excluding out is the address. Though in real work, address will not be important. You have to drop such information because that's so specific for a particular user. Imagine getting this data to somebody who wants to harm. So make sure that you don't have, though this is not directly useful because there is no human being, but because these are detailed, if you can trace this address, you can get the person. So you have to be very careful to having information about user in your data. So just the same thing, before we just dive into that, you can check your data the way we have always been doing. Df dot columns, how many columns do we have? All those things should still be done on any data set you are working with. Df dot shape, how many records do we have? We have about 5,000 records here. You can see this is more data. Df dot info. Oh, there are no missing data here. Can you see this from here? There are no missing data, so that means that's good. Df dot duplicate, I doubt there will be that. Is it duplicated now or what? So first, there are none. Okay, so I can go on and on to do df dot correlation. Of course, for this kind of task, yeah, this will throw error. Why? Because there is address there. All right, there is address there. So I can ask this to do for only numeric. I know address is not. Let me see if this method can work here. No, it doesn't have anything like this. So let me do shift tab and see the possible guys here. So you can see here from what I have, I can say numeric only. Numeric only. Let me put that here if it works. It said numeric only is not defined. So let me check the way it was used here. It's saying this does not exist. So I need to go online and check for this because what I want to do, that's why I'm saying you don't need to cram any code. So I want to how to use correlation on only numeric features only. Let me share this part so you can see. So I'm asking Google how to use correlation on only numeric features only. So I'm showing you this so that as far as you know what you want to do, all right, you don't have issues. You can see this is what I tried doing. Okay, so you can see however it says I should do numeric only true. And you can see that this was what I was trying to do before and it was throwing error. Let me come back to my screen. Let me see if this is going to work. Yeah, so you can see this now. Can you see that it's worked now? So these things are not difficult. You just need to know what you want to do and you want to take note of how to go about it. And as I'm showing you, you know, what I'm doing. So you don't need to cram any code, all right? You don't need to cram any code, right? You don't need to cram any code. So that's what I just showed you now. But you know what you want to do, and you know that correlation will only give us features that are numeric, all right? So from that now, we can check this. What does this mean? And from the way you can see, what the target here is the price. So you can look at all of these guys housing. So from here, you can see that the average area income has effect on the price of a house. And this is already showing us about 64%. Average house age, that is how long the house has been there, has about 45%, which is high correlation. The average area number of rooms in that area has about 34%, impact or importance. Average number of bedrooms also has about 17%, which also means, so average population, how much people stay there, has about 41%. All right. I'm just showing you these are the things you can still do when you have any data. All the things we've done before, you can repeat them again. You are supposed to repeat them again, because every data has their uniqueness. Every data has something unique about it. All right. Every data has something unique about it. You can see it's not too difficult. Okay. It's not too difficult. It's just that you have to know what everything we are doing means. Once you understand what they mean, you will be able to replicate them back. You'll be able to try them back. Is that clear? So just to show you this, as we move on, and let's say I want to draw, let's say you want to also get the, let's say you want to also make, you want to, like what we did here before, maybe you also want to do this plot again. All right. It's still the same thing. So it's not as if it's anything difficult. So let me come back here before we continue what is happening here. So here, if I paste this guy, so I just have to put this numeric only inside what I have here. So this code will still, then I have to be sure this I've imported Cbon. Let's confirm Cbon is not there. So we need to do import Cbon as SNS. I need to rerun this page. I'm just trying to show you all of these because they are not difficult and you might need to do them again based on whatever you are working with. So if I come back here and I run this guy, you should be able to plot that for me. Okay, you say, are we using matplotlib somewhere? Okay, this plot is coming from matplotlib. So I will import matplotlib too. This is just showing you some of the things that are happening. Import matplotlib dot plot as plt. Nobody call matplotlib dot. That means I might not be importing in the right way. So I don't need to stress myself too much. I can always come back and you see that my y is missing there. So writing the code is not the problem. Just have an idea of what you are trying to do. Can you see? That corrected the error I was having. You can see I'm doing a lot of things and I'm not trying to cram too many things. But I know what my errors are. You can see I'm getting the same result almost like what I had earlier. Okay, so with this, let's continue performing our scaling on what we have. Here we want to try out absolute maximum scaling. Somebody has asked before, which one should we use? You try as many. It is how your model is doing. You say, this one is not necessary. This one did not do well, and all of that. So to do that, for maximum absolute, we say np.max, np.absolute for all our data. Axis equals 0. Please note, axis equals to 0 means you are working with the row. Axis equals to 0 means we are accessing the rows, which is the same as record. Same as records. Y axis equals to 1 means we are accessing the column. This is very important too, because people will still ask me, and people mix this up a number of times. Okay. So here we have maximum underscore ABS. That's what we have here. This will help us to calculate the maximum absolute. Then to the scale ID is going to be the DF, which is where our data is, divided by maximum absolute. So if we do scaled underscore df, this is not the new data we're going to be working with. We won't be using df again, because scaled df is not the one we have, is not the guy that we have what we have scaled. So df, we have done with that. So moving on is this guy we'll be using now. Is not this scale df we'll be using. What are our issues? Bad operand type for absolute string. What is happening here? Unless I don't even know what these issues are. All right, that's why the internet is there, to help me to solve such kind of issues that I might have. Now, you don't forget that there is a column. If you remember, there is a column that has what? There is a column that has, what do we call it now? There is a column called address that I did not, don't forget that we still have. All right. So for me to undo that, I'll come back to this guy here. Okay. To undo that for me. You can see this is only going to help me to work with only numeric, all the ones that are numbers. So I won't have all this issue I'm having now. And even if I don't want to do this, I can just drop my my address from the data. I can just drop my address from the data. So how do I drop? Now the question is, do you want to drop permanently or drop temporarily? If I go back to some of the codes we have used in yesterday class, I will see how to drop a column. You can see it's not too difficult as far as you have an idea of what you are trying to do. All right. Something like this is what I'm going to need. Something like this is what I'm going to need. So if I come here, I could just do this. Drop, what is the name of the column? Instead of saying columns, I don't need that. So if I want to drop a single column, I'll just do this. What's the name of the column? I'll come to copy the name of the column, which is address. So I won't be having the issues I'm having. It's left to you. All right. So if you do this, so I do the f.columns, you see address is not there for now. So the issue I'm having now, I won't have. So I don't need this one again. If I just do my df dot, if I just do my df dot correlation, you can see doing the same thing in different ways. All right. So it's all left to you and what you think works for you. Can you see I don't have that issue again now? Can you see if I remove all these? But you can see you've learned something new again. All right. That's the beauty of coding. One thing can't just be done one way. So if I run this now, that issue is gone. Why? Because I no longer have that guy. So you can see with this, it has scaled for me. All right, my numbers now. I've used my absolute maximum scaling to undo it. So now it is this scaled df I will be working with into my model. Another approach we can use is minimum max. We've used this before, which is commonly to get a number between 0 and 1. Also, it's also sensitive to undo outliers. So what do we do? Same thing, from sklen.preprocess, import minimum max scalar. We call this scalar, we fit it into our data frame here, and it should also still show the name of the columns. So here now the scale df is this guy. You can see same thing, but we have used a different method. Well, another approach we can use is vector normalization. Very close to what we have done before, just calling which one are we using, and we perform that on the data. That is, different ways of normalizing and scaling our data. Any question on scaling and normalization? We have done that before. Yeah, somebody's asking boolean values, and yeah, boolean values are non-numeric. Yeah, that's correct. That's like another one. Yeah, what I meant was if you type numeric only to be false, won't it shows boolean value? Yeah, it will. That means you are saying everything opposite number is what you want to get in your result. Yeah, so that's what that means. Okay, so with this we can move to feature extraction. So what is feature extraction? Feature extraction is the process of transforming raw data into a simplified, informative set of features. This reduces our data complexity and highlights the most important and relevant information, making it easier for machine learning models to analyze patterns and learn efficiently. Feature extraction also involves model accuracy, reduces computational cost, and focus learning on the most essential aspect of the data. We've talked about the importance already. So what are the key techniques for feature extraction? We can use some statistical methods for that. We can do dimensionality reduction. We can so choosing the right method. One is what type of data are we working with? What is the objective of your machine learning task? What is the available computational resources? What is domain knowledge and experts saying about it? At this stage that we are using rows and column data, we have been working with tabular data. Take note of that. The kind of data we are working with at this stage is tabular data. So most of the things we have been doing works pretty much well for tabular data. And the kind of tasks we've been doing so far, they are tabular kind of data that we have been working with. All right. So we are working with tabular data. Must we carry out the two on our data? Not necessarily. It depends on you and what you want to try out. At times, you might not even need to do it on the data based on when you continued without it and the model still did well. So these are just the experiments you should try out whenever you are cleaning your data, processing your data for the model. You might not even do all of this, all right? But the beauty is that you try it out. The beauty is that you experiment, so that when they ask, what have you done on your data? Because if you come to ask me, oh, Mr. Israel, my model is not working well, these are things I'm going to ask you to do. Have you scaled your data? Have you experimented it? Have you normalized it? All of these things has effect on the way your model performs. They have effect on the way your model performs. Okay. So what are challenges with why we need to choose feature extraction? Information loss and computational complexity. When we are loading more data, just our system CPU might not be able to handle the data. That is why we are recommending that you should know how to use Google Code Lab. You should know how to use Google Kernel, because at this stage you might have very heavy data. I've worked on projects before whereby the data size is about 1 terabyte. My system can run such. I need to get a GPU on the cloud to do that. I have to use a Google Cloud to do that. So that's the same thing even for you. As you begin to work, it's not every time that your data, will be like that. I've told you which one should you use. You try them out. the one to use is based on what works well on your model. That's one. Two, make your research. Ask questions on the internet. Which one do you recommend? Which one when do they ask us to use this? What kind of data can we use? So these are the other things you can, do research on, all right, to know. All of what we do in machine learning is experimental. So you don't just sit down and say this is what to do. You try it. You can see the number of things I've been trying, just trying to clean my daughter. All right. So you try as many things as possible out. Somebody is asking, what if it's categorical, not numeric? You need to first, I've told you that before, though we have not done it, but you need to convert categorical to numeric. We're still going to talk about that encoding as we continue our feature engineering. Okay. So the things you can do in feature engineering, one is that you can create a new feature, you can transform, and the transformation is what we're already doing. We have done a part which is normalization and scaling. There's somebody who is asking about when we have categorical feature, so we can encode them. All right, and we're going to learn about that at this point. We talk about feature extraction and feature selection, then feature scaling. We've talked about feature scaling already. We've talked about feature um, transformation specifically for numeric. Yes, at the moment. So we'll talk about a few more other ones as we move on. So let's talk about feature selection. There are several ones we can use for feature selection. We have filter methods which we can use on each feature independently of the model by measuring its relationship with the targets. They are used during preprocessing to remove irrelevant or redundant feature based on statistical tests or other criteria. We also have the wrapper method. We have the embedding method. All right. So how do we choose? Based on the data size, based on the model you're trying to work with, based on the interpretable needs, and finally based on your computational resources. Time does not permit us to start talking about these guys one by one, but just be aware that they ever exist. We're still going to use some of them as we continue to work anyways, but this is just to prepare your mind towards the things you should have done on your data before you can even take a model. So you can see the things we are doing, even though the goal is to build a model, even though the goal is to build model, but you can see the number of things we've got to do, as it were. So from tomorrow's class now, we'll be able to build our model. After that, we understand some of the preprocessing that we can decide to do on our model. So let's stop here today, because I know we have said a lot of things that are pretty very new and that we still need time to digest them. We can take the remaining of the class at our leisure to take note of them. But you can see since yesterday, all we have been doing is to prepare us for building machine learning model. And so that means you can't just wake up and say, I want to build model and start doing. No. Before you can build a model, you can see the things we have to. You can see why we said that 70% of the real modeling is on cleaning your data. Performing dimensionality reduction, yes, it's also feature engineering, because it has to be, it's under feature extraction too. But because, like I said, we cannot look at all these methods. As we begin to work, we will come in contact with these methods. As we begin to work, we will use them. But we cannot, we don't have all of the time to look at all of these guys one after the other. So please take note of the things that we have learned. I know some of these things you might be hearing them for the first time, but as it were, they are not difficult. But know that they exist. And that is why I have taken out time to create this material to focus on the main thing, at least that you will need. As much as there are many things outside that you still need to look at, but at least what we have here can start your machine learning model classes and all. So another question before we call it a day. So by tomorrow, we'll be able to build our first set of models, since we now have done, to a logical extent, we understand the preprocessing we're supposed to have done on our data. So any other question? before we call it a day. All right. So if there are no other question, please advise. You see, I'm not giving any tax yet because there are many tasks to give you. But at this moment, you have to understand what exactly we are doing. You have to understand exactly what we are doing. So at this point, please go through the videos again, take your notes, understand the peculiarity of all of these methods. And that's the big thing. Once you know what it means to say we are cleaning data, once you know what it means to say we are preprocessing data, you will be able to understand what you need to do, per time. So on this note, thank you for joining today's class. We meet again tomorrow, and tomorrow we go more deeper, but it's not difficult at all. Most of the things I already mentioned. What is asking does somebody says, does correlation input into choice of feature eventually? Yes, of course. From what you can from what we have done, that can also inform us about what we can do. Yeah, somebody saying that a lot, obviously. It's a whole lot we have spoke about, trust me. And if you take note of them, it's going to help you in the data journey. And that's why I'm trying to stop here so that we don't go beyond this. But at least what we have done so far between yesterday and today, you are good enough to understand your preprocessing, and you are ready for tomorrow's class, which is on modeling. So that being said, thank you for joining. See you in tomorrow's class. Good night, everyone.